Thank you for attending my presentation. I'm Jae Shim from Seoul National University, and today I'm going to present about fault diagnostics in electric drives using a machine learning. This is the outline of the presentation. First, I will introduce the background of our research, and I'm going to talk about the fault analysis for insight of selecting input variables. Based on the analysis, I will propose a design of artificial neural network for fault diagnosis. It will be verified statistically and experimentally in section 4. And finally, I will talk about the conclusion. I'm gonna talk about the background of our research. As vehicle and urban air mobility have been electrified these days, the need for fault diagnosis for electric drive is growing for stability issues. Furthermore, finding the faulty part in the electric drive system is costly. Therefore, we propose an electric drive fault diagnosis model using a machine learning model. The reason to use a machine learning model is as follows. Many types of research about fault diagnosis have been focused on the model-based algorithm. However, if we want to diagnose the multiple types of faults, all the algorithm must be implemented on the DSP. In contrast, a method based on the machine learning model can solve this problem by retraining the diagnosis model. Next, I will introduce the target of this research. First, the characteristics of the target system are represented in this table. 200-watt SMPMSM with 8 poles is used for this research, and IGBT power module from Mitsubishi is used. In this study, two types of failure are dealt with. The first one is the current sensor offset and scale error on A, B, and C phases. The second one is the switch open fault condition on A, B, and C phases. In other words, one normal state and 12 fault conditions, a total 13 types are to be classified in this research. When diagnosing using an ANN, the classifier's performance is greatly influenced by which data is used. Therefore, to determine the data type, this page presents a sample analysis. This result shows the analysis on the current sensor error. As we can see, currents in the synchronous reference frame have a vibrant and offset error like this. Therefore, we can obtain the insight that if we train the DQ current error on the SRF, we can diagnose the failure. This is the analysis results of the switch open fault condition. In a switch open fault situation, the synthesizable pole voltage varies depending on the current direction and whether the upper or lower phase is faulty. As a result, when the pole voltage error is converted into SRF, it shows that voltage have error in SRF. Therefore, by this analysis, we can obtain the insights that if we train the DQ voltage error on the SRF, we can diagnose the switch open fault conditions. There are experimental results to see how the failure situation analyzed before are observed in the actual system. For simplicity of expression, only the command actual value and error of the Q-axis on the SRF are shown. The situation sequentially indicated from A to E is as follows. As previously analyzed in the current sensor failure situation, it can be confirmed that the error that appears during one electric angle is 1 or 2 times the fundamental electric angle frequency, like these figures. In addition, we can observe that a current error occurs severely due to a voltage error in the switch-off fault condition, as we can be seen in D and E. This page shows how to acquire the previously mentioned data types. The left figure shows the driving profile for data acquisition. This is one of the profiles used in this research. For training a general model, profiles for training and testing are set differently. And the reason for creating such a dynamic profile is that the drive motor does not operate only in a static state. Data are obtained at interval of 60 degrees in SRF like this figure. Staking is performed while sensing 6 times in one electric period. Reason for acquiring data only 6 times is for reducing the computational load on DSP. In order to diagnose even in dynamic state with the previously mentioned data, speed and torque are also measured at 0.1 second intervals. This is to recognize the acceleration or deceleration situation. The data acquired as shown in the above figure are used in the ANN model after normalization. In this way, this ensures that learning is performed well by matching the scale of values to similar levels. This page represents the results of the analysis of input data. This analysis is for finding the best combination of the data to be used in the diagnosis model. It shows the performance according to the data combination and the limit of the motor output. The overall experimental results are evaluated as follows. First, if learning and evaluation are performed based on all acquired data, the diagnostic accuracy can be achieved only up to 97.48%. And overall, it can be seen that using Q-axis information is good for diagnostic performance. As suggested in this study, it is confirmed that in dynamic situation, the data combination including speed and torque together, like this, achieved higher performance than other data combinations. If we select the best model, as we can see in the green colored area, the set of number 6 data set with 50% output boundary achieves the highest performance. Therefore, from the following slides, the experiment is conducted using this number 6 data set with 50% output boundary. Although not shown in here, higher accuracy could be achieved by setting the boundary threshold higher. However, in the case when the output is small, the diagnosis becomes impossible, and there is also a problem that the effectiveness may decrease. Therefore, in this study, the speed and torque boundary are set only up to 50%. The reason that the diagnosis work well in such a large output situation is that the error value occurs relatively clearly because the size of the control variables are large. Next, we'll talk about the structure optimization process of the ANN. Optimizations are done for the diagnostic accuracy and the number of parameters used in the model. If the number of neurons in the model is large, it is highly likely to extract deep features well and improve classification performance. However, neural networks computation load increases dramatically on the DSP. Therefore, it should be optimized. This is the result of the experiment with accuracy and parameters according to the number of nodes. Initially, we got 99.66% with 20 nodes, but we can get a 99.06% result even with 10 nodes. Therefore, considering the computational load on the DSP, the number of nodes in each layer is determined to be 10. The right side figure shows the structure of the final proposed model. Acquired target data are normalized and then are input into the ANN. Each layer has a value activation function, like this. And then, after calculating the ANN's final layer with softmax output, the predicted fault ID. This page represents the statistical evaluation results. The first one is confusion matrix, which represents how to predict true data. The larger the number on the diagonal, the better the diagnostic model is trained. As we can see in this figure, the size of the diagonal components is larger than the size of the other components. It means that the model training is successful. The second figure represents the classification evaluation metrics. These are statistical indicators calculated from the results of the confusion matrix. It can be seen that the precision and recall for each class have about 97 to 99%. F1 score is weighted average of precision and recall. Therefore, by looking at the F1 score, precision and recall can be observed comprehensively. And accuracy means the proportion of the data correctly classified by the model. In here, overall 99.06% accuracy is achieved. This page shows the REST evaluation results with the statistical evaluation results, which are previously mentioned. This page shows the algorithm verification on the TI 2A379S DSP. For this verification, parameters are extracted from the trained model, and then an ANN model is built on the DSP with the extracted parameters. Operation for testing is done in both steady state and dynamic state. This is the experiment set. And the right side is the result of the algorithm verification with 200 watt PMSM and the DSP. The first result is the results of the experiment in the normal state. And second one is in the A page current sensor scale fault condition. And third one is the A page current offset fault condition. And last one is the result of the A page top switch open fault condition. Overall, we can see that the DSP predicts the fault states well, like this. This page is the last page of this presentation. The proposed model in this study will be briefly summarized. The proposed model has an ANN with 2 fully connected layers and 10 neurons in each layer. It raises the difficulty of designing the diagnostic model compared to the previous model-based algorithm. This model's statistical diagnostic accuracy is 99.06% for 50,337 datasets, and its performance on TI-28379S DSP is also demonstrated. Thank you for listening my presentation.